Hello everyone, my name is Saba Masriya and I am from the Department of Electronics Convergence Engineering. Today I'll be summarizing a research paper titled Tailored Bifunctionalist Biosensor for the Level-Free Sensing of Prostate-Specific Antigen. In this presentation, I'll talk about why this work is important and I talk about the methods here used and experiments and the main results showing that these sensors can quickly and accurately detect PSA. This article talks about the growing need for smart biosensors and introduces a new capacitive biosensor for detecting PSA, which is an important marker for prostate-related diseases. The biosensor uses a small interdigitated capacitor design and is bifunctionalist, so it can detect PSA without needing extra levels. And it works fast, like just 3 seconds, and can detect PSA at very low levels between 0.1 and 10 microliters per milliliter. And this sensor is also highly selective, repeatable, and reusable, making it a cost-effective and practical choice for real-time testing and diagnosis at clinics or even on site. Prostate cancer is very common in men, and one way to check for it is by measuring PSA or prostate-specific antigen. PSA levels often go up when cancer is present, but they can also rise because of other prostate problems, which makes it hard to diagnose accurately. The standard PSA tests like ELISA or fluorescence tests are accurate but expensive, slow, and need special lab equipment. This shows a clear need for a cheaper, faster, and simple test that can help with early diagnosis. In this study, a small biosensor was developed using an interdigitated capacitor coated with biological materials to detect PSA. This sensor is fast, giving results in just 3 seconds, reusable and low cost, under $5, making it ideal to point-of-care testing. In the experimental section slide, in this study, and this slide shows the experimental procedure of the PSA biosensor, and here materials used include PSA protein and anti-PSA antibodies and chemicals such as APTS, PBS, ethanol, and deionized water. The biosensor is a mini interdigitated capacitor with 24 fingers fabricated on a glass substrate with titanium and platinum layers. The surface was first cleaned and with piranha solution and then coated with epitape to introduce amino groups. And here PSA binds to the antibodies, causing a change in capacitance, which is measured using an LCR meter at 1 kHz. Concentrations from 0.1 to 10 microliters per milliliter were tested, and the sensor responds in approximately in 3 seconds. Characterization of the surface and chemical layers was done using AFM, SEM, and FTIR. The sensor shows high sensitivity, selectivity, and reusability, enabling real-time level-free detection. The capacitance changes are explained by variations in charge distribution, dielectric constant, and conductivity. Overall, this experimental setup allows fast and accurate detection of PSA. This slide presents the results and discussion of the ITC biosensor surface. Surface changes were analyzed using capacitance measurements, AFM, SEM, and FTIR. And APTS coating introduces small gaps on the surface, causing tiny changes in capacitance. When anti-PSA antibodies are added, capacitance increases. The titanium or platinum electrodes performed well here, and they are cost-effective, so easy to fabricate and flexible. Modifying surface layers allows detection of different PSA concentrations. AFM was used to examine surface roughness at different stages like bare chips, chip with antibodies plus PSA. This shows how the surface changes step by step during preparations and PSA binding. FTIR confirmed the presence of chemical groups at each stage, while FEM showed surface structure changes after coating and PSA binding. For FEM imaging, the chips are cleaned and coated with gold or palladium to improve visibility. Overall, these results confirm that the surface modifications and electrode design effectively support PSA detection. This slide covers PSA detection in human samples as well as the sensor selectivity and usability. PSA detection was performed using real human semen samples. Change in capacitance. The response time was very fast, around 3 seconds, making it suitable for clinical applications. In terms of selectivity, the sensor specifically detects PSA even in the presence of other proteins or chemicals such as glutaraldehyde, and capacitance changes occur only when PSA binds, confirming high specificity. The sensor also maintains stable performance for at least 15 days. For reusability, the sensor can be cleaned with piranha solution and reused at least 3 times without loss of performance. Capacitance remains stable, reproducibility is high, and sensitivity is maintained, making the sensor cost-effective for repeated clinical or laboratory use. Overall, these results demonstrate that the sensor is fast, selective, and reusable, which is ideal for practical applications. This slide summarizes the main conclusions of the study. A label-free capacitive IDC biosensor was successfully developed for PSA detection. The sensor provides first detection, measuring PSA within 3 seconds. It operates in real time and is suitable for point-of-care diagnosis. Only a very small sample volume is required, and the sensor demonstrates high reproducibility and stability over several weeks. It is reusable, which reduces costs and makes it practical for multiple tests. Beyond PSA, the sensor has the potential to detect other biomarkers, supporting early stage and personalized diagnosis. Its miniaturized and stable design allows application in rapid and sensitive disease management. Overall, this biosensor shows promise for large, reliable, and cost-effective clinical applications. That's it for now. Thank you for listening.